Hey there. If you've spent any time with physics, you've probably run into a problem from Irodov's collection and just stared at it, right? They're famous for being tough. But today, we're going to tackle problem 1.96 together, and I'm going to show you how one single, really elegant idea can just slice right through all the complicated stuff. Let's dive in.
Okay, so this is the challenge. We've got a body, mass m, thrown with some initial velocity, v0, at an angle. The problem asks for two things. What's the change in its momentum after some time t? And what's the total change in momentum over its entire flight? Now, I know what you're thinking. You're probably picturing breaking down vectors, calculating trajectories, finding final velocities. But hold on. There's a much, much simpler way to do this. We can solve this whole thing by focusing on just one core idea.
And that key, the thing that unlocks this whole problem, is the relationship between impulse and momentum. Seriously, forget about calculating the object's final velocity for now. This connection is our secret weapon. It's going to let us bypass all the difficult steps.
So let's really think about that. When a physics problem specifically asks for a change in momentum, what concept should immediately pop into your head? Well, let's break that down.
First, you've got momentum. We all know it, right? Mass times velocity. But the really critical thing to remember, always, is that momentum is a vector. It's got a direction, not just a number. As that body flies through the air, its velocity vector is constantly changing, which means its momentum is constantly changing too.
And next, we have impulse. You can think of impulse as the reason momentum changes. It's simply the net force acting on something multiplied by how long that force acts. It's kind of like the kick or the push an object gets over a period of time. And just like momentum, it's also a vector.
And this is where the magic happens, the impulse-momentum theorem. It tells us that the change in momentum, delta p, is exactly equal to the impulse. It's not just related, it's the same thing. This is the key that unlocks everything. Instead of tracking the complicated changes in velocity, all we need to do is find the net force and the time.
So let's put this amazing tool to work on the first part of our problem, which asks for that momentum change over the first t seconds of motion.
We're going to follow a super simple three-step plan. 1, we'll find the net force. 2, we'll figure out the time interval. And 3, we just plug them straight into our theorem. It's honestly that easy. Okay, step 1. What's the net force? The problem gives us this giant clue, this gift, really. It says assuming the air drag to be negligible. That simplifies everything. With air drag gone, the only force we have to worry about for the entire flight is gravity. And that's just a constant force, mg, pointing straight down.
Step 2, what's our time interval? Well, this one's even easier. The problem just hands it to us. It asks for the change over the first t seconds. So our delta t is just t.
And finally, step 3, we just put the pieces together. We apply the theorem. The change in momentum, delta p, is simply the net force, mg, multiplied by the time, t. And since force is a vector, our answer is also a vector. It has a magnitude of mgt, and it points in the exact same direction as the force, vertically downwards. And that's it. That's the answer to part A.
Now, let's pause here because this is a really important point and a classic trap for students. The question asked for the change in momentum, delta p, not the final momentum. It is so tempting to get bogged down in calculating complex velocity vectors. But look at our answer. It doesn't depend on the initial velocity v0 or the launch angle at all. For part A, all that information was just noise, a distraction. Our method let us ignore it completely and go straight for the answer.
All right, now for part B. The question asks for the modulus of the momentum increment. Don't let that word scare you. It's just a fancy way of saying its magnitude or its size. We need the size of the momentum change over the entire trip. And the best part, we can use our exact same theorem. The net force is still the same, right? It's just gravity, mg. So the only new piece of the puzzle we need is the total time interval. The question is, how do we find the total time the body is in the air?
Well, for any standard projectile motion problem like this, you might remember the formula for the total time of flight. We'll call it tau. It's twice the initial vertical component of the velocity, vye, divided by g. And that vertical velocity is just v0 times the sine of the launch angle, alpha. So the total time is 2 times v0 sine alpha, all divided by g.
Now we just do it again. We apply our theorem one more time. The magnitude of the total change in momentum is just the magnitude of our net force, mg, multiplied by that total time of flight we just figured out.
And just look how beautifully this cleans up. The gi in the top and the gi in the bottom just cancel each other out. And that leaves us with our final, elegant answer for part B. The total change in momentum has a magnitude of 2 times m times v naught times sine alpha. Simple as that.
So we did it. We conquered Irodov 1.96. But let's zoom out. What's the big picture here? What's the lesson we should really take away from this?
Here's the deal. The impulse momentum theorem isn't just a formula, it's an incredibly powerful shortcut. The change in something's momentum is driven only by the external forces on it and how long they act. That's it. As we saw, that meant for part A, the initial speed and angle were totally irrelevant. They were just there to distract you. So the real test of a problem like this isn't just being able to do the math, it's about spotting the most direct, most powerful physical principle you can use.
And that brings us to a final thought to chew on. What if our net force wasn't constant? What if our object wasn't a simple body, but a rocket that's actually ejecting fuel, changing its own mass as it flies? How would you apply the impulse momentum theorem then? Something to think about. Thanks for joining me.